So we can change the columns, and then the thing of determinant can change, but not the module. So so only thing can change, and we get this matrix. Next, it will be A0, A1, etc. A0, A1, AN-2.
Are you sure you want AN-1 in the corner of your matrix? Not A0.
Oh, okay,
Like
yes, okay, it does not change a lot, but okay, maybe it's better if we so we don't touch the first column, and we just change other columns. It will be like this. Also we can transpose it. So now it will be this one. Okay, so now I want to say that vectors of such form oh, no. One, that these vectors are vectors. And finally, to the power n-1. So it is okay, because we have that it is equal f of this number multiplied by the same. So here we have n distinct eigenvectors with eigenvalues, and the determinant is the product of these eigenvalues.
So maybe say something more about why does this formula holds?
Okay, for example, we have that an-1 plus a0 and 2k plus a1 and 2k, etc. I look at the second line. We can okay, so if we multiply this by zeta n to the minus k. Yes, when we have f. Okay, just a second. Yes, when we have so this is not true. Oh, no. Sorry. Yes, it is true. So my formula here is not true. Oh, just a second. So we have. So okay, that's all.
Okay, so we have explicit eigenvectors with explicit eigenvalues, and everything's fine, right? Okay, so the next problem is
okay, so I want to show that.
oh, oops. No, everything's correct. Okay.
Oops.
So we want to prove that odd Bernoulli numbers are all zero.
And you mean that we should do this before, like proving this logarithmic formula? It's
Yeah,
about
of course.
even numbers, yes. So I can try to do it в лоб using like подстановка ряд в ряд.
What do you mean? So what?
I mean,
what is your plan?
There is like t divided by, or I am not
So we
writing.
have an exponential generating formula for Bernoulli numbers.
Yes,
then?
like t divided by e to the t minus 1. And then we can like say that we can take this like t divided by some x minus 1. So there is like a formula that it's t multiplied by 1 plus x plus x squared plus etc.
What are you trying to do?
And now I can substitute a series for this in this.
And what do I don't understand what.
And calculate coefficient if it's like not doing
the Bernoulli numbers are rather tricky to compute actually. So
Yeah,
so
okay.
you would be
So-
able to compute like the recurrent formula, I guess, but this is not what you need to prove that all
Yeah.
the odd Bernoulli numbers are zero. So
Oh,
So you need to prove this
suppose that-
function is odd. Oh,
so
sorry,
you need to
even.
prove that
we
certain
need to
function
no
is
no
even.
not this function is odd, because as we remember, b1 is what on the lecture was 1/2
B1 is -1/2.
minus 1/2. Yes, so we need really to prove that t divided by e to the t minus 1 plus t to the half is like what is
Even.
even.
Mhm.
I really love this example a lot because it's a non-trivial example of an even function, in my opinion.
Like, let's say that this is like f of t. Now we have f of minus t. And maybe we need to subtract f of t for
Let's
to be good.
first compute f of minus t. What is f of minus t? Let's try to figure out.
It's
what
just
is
like
f of-
place minus t every. Like f of minus t is
I mean, let's try to simplify the expression a bit.
Mhm.
like for simplifying this, I can multiply both here by e to the power of t. I think that it can help.
So what you will get from this?
Кручу, верчу, запутать хочу. Multiplied by e to the power of t, and there will be plus. Ой, зачем я все? Sorry, I think that it's not necessary to. Like 1 minus e to the t minus this. So then I can like say that it's e to the t multiplied by this thing that we have here, and minus t divided by 2. And now we can see that if we subtract like so, this was about this, and this is equal to e to the t minus 1 multiplied by this. I can remember that I did this before, but I can't
Okay, so
remember
so
well.
you subtract and what happens?
So this and this cancels out, and we get 0.
How?
There will be t remains.
Okay.
That will-
Here I can see. Okay, so all odd Bernoulli numbers are zero except for the obvious one. And what now? Now we need to prove the identity for certain logarithm of an exponent, right?
Mhm.
How do we do it?
I think that it's automatically from this.
How?
So what does it mean? There is like there is
No.
some 2k from in denominator, and I can't and okay, no, of course it's kind of obvious. So oh no, why this function. Yes, so we have like this expression. Sorry.
Mhm.
This should be like negative logarithm of a flipped thing.
Mhm.
Minus like if this is flipped thing, so we can like remember that it will be exactly our thing. So
So-
sum from 0 to infinity b 0 bn to x to the power of n divided by n. Yeah, and minus x divided by 2. And as we know, like we need to count only. We need to count only for odd or for even things. So it will be things like for 2k, because this cancels down, so we can.
Sorry, how we get this formula? We lose logarithm somehow.
Yes. Oh, it's my mistake. We lose logarithm somehow. Wait a minute. Like подстановка red. I didn't realize there was logarithm, but this logarithm will give us this 2k extra in denominator.
How?
It's just my наблюдение from answer, observation from answer.
Let's try a different thing. What will happen if you take a derivative of your function?
Okay. I'm taking derivative of this. Excuse me, logarithm is like this, yes?
Right,
Or not?
right. Absolutely correct.
I think it's bad, but we'll see. So we are taking like this, yes?
Mhm.
So we can begin with this, and then like minus x-1 and minus 1/2. Maybe we will be able to collect like x minus.
Wait, what?
We should divide by e of x minus 1.
Yes, I forgot that there was this logarithm again. So on
So the
denominator,
square changes to
Yeah,
x.
you are trying to
yeah.
insist on forgetting the logarithm.
Yes. Who cares about logarithms nowadays? So, like, I don't know. I want to expand this maybe. Yes, it's nice. It will be like e to the x divided by e to the x minus 1, and I know what to do with this. Minus very strange thing. Like this. Yes. So I think that we should rewrite this using like. Oh no.
Did you miss an X somewhere? Ah, no. Oh my God. Wait.
Correct, but this thing is not what I want to see here. Maybe I missed something.
Oh no, I guess it's fine.
It's fine.
We
Thank you.
will see what will happen.
So,
Ignore the 1/2 and subtract 1 from the first summand. The first summand.
what? Yes.
The first summand is 1 plus.
I see there is like 2 ways to simplify first summand, and you want me to say that it's 1 minus
1 plus.
Wait,
1 plus.
1 plus 1 divided by this thing.
Yeah. Then
sorry, maybe we should multiply by x, divide by x, so we have 1 minus x multiplied by this Bernoulli series. No, you have it.
yeah, it's a correct way.
What?
So if you multiply this thing by x, you are going to get the Bernoulli series minus 1 and plus x over 2, right? Something like this.
If I multiply this by x, I will get, there will be, yes, really. So this whole thing is equal to 1 over x multiplied by this Bernoulli sum. From 0 to infinity. But we start not from 0, but from 2. Yes, I think that yes.
What?
Like subtracting.
You get bn over n factorial multiplied by x to the n. No?
Well, I forgot, or this wasn't. Yeah. So just let's write this without the strange brackets.
And so this is the same series that you will get if you differentiate the presumable answer, right?
If I will differentiate this, I will get like, yes, odd, like we have only odd coefficients. And if we differentiate, yeah, I can see this.
Okay, so is everything clear with this problem?
I think yes.
Any questions from anyone? If not, let's move on to the next one. What is the next problem?
All right, so the next one is about
I
Bernoulli.
can try it, but I'm not sure that I will succeed.
Let's try. Okay. It is about the Bernoulli polynomials.
Mhm.
Yes. Mm. Mhm. Oh, sorry. So we have that our Bernoulli number is the value at 0 of this polynomial. And as far as I remember, we have such formula which want to prove maybe that oh sorry, it's polynomial, that the derivative of it is behaves like a derivative of
No, this is not a problem from the similar problem set, but you can prove it if you
I mean that from this we can easily check that this next formula, because it's like a Taylor expansion of polynomial. So we have that it is the sum. It is equal, I think. So our main task is to show that. So we have this is Taylor expansion at 0. Xk. And so we see that these formulas are equal. I mean, it is equal that this is k0 to n k. I mean, if you compare these coefficients, this follows from the previous one. Yes. So we want to prove this formula somehow from this generating function.
Yeah. So all you need to do is differentiate your generating function.
Okay. So let me do it.
Over x.
So it is equal to t square, and then just the same.
Yeah, so express it as
Okay, okay.
the generating function.
T minus 1. So it is I mean, here we write t to the n, and here it will be bn minus 1 x, and here divided by n factorial, and also we should multiply by n. So we get our formula, and maybe we should look at n is equal to 1 and 0, but I think it will be true. So this is the first formula.
Correct.
Mm,
Yeah, so the expression of Bernoulli polynomial is correct. Now, how do we establish the second one, which is the formula for the sum of powers?
Do we want to use our first formula? So are they connected, or these are two separate exercises?
No, these are two separate exercises,
Mhm.
of course.
Maybe we should try again, look at this generating function
So let me propose something. What will happen if we apply our formula for m and then for m+1?
it will be difference of this degree series.
What?
You mean if we take big M and big M+1?
Yeah.
It will be just one. Oh, okay, I will try. So we want to prove that b n+1 m+1 1 n+1 divided by n+1 minus the same for m that it is equal to m big M to the power n. Yes. Okay.
So wait, what? Yes, this is what we want to prove. If we were able to prove this result, then everything else follows by induction, correct?
So maybe here is here minus but n+1 is for the case when m is 0, 1. So, but in general case we have.
What?
I mean, it is not clear why we have this.
This term is needed so that our formula is true for m equals 0.
So I meant the same. Okay.
So the zero term, the free term corresponds to the base of induction in this case. Okay.
Okay. Oh, maybe now we should finally use our formula. So we have T x is m+1
Yeah, so if we plug this difference into the generating function, we get something like
let me see. We have this function. So it looks like it looks very similar to what we wanted to have.
yeah, not only similar, this is just the same. Yeah, you should also account for the fact that you take bn plus 1, not bn, but still, okay, so it's kind of clear that we are going to get this result. Okay. So the next problem is about the von Staud-Clausen theorem.
We have 3 minutes left,
Ah, okay.
and
I guess it's okay if we finish that here, right?
yep.
Right.
We've solved some problems, and we were quite productive today. Thank you very much. As usual, some problems are left, but they are quite clear today. Quite easy, I would say.
Okay, thank you.
Okay, bye.
Okay, bye.
Bye.